Okay, thanks. So I will be presenting on behalf of uh, many of my co-authors from these institutions shown here on hls4ml, which is an open source co-design workflow for scientific low power machine learning devices. So first, let me introduce a bit our motivation and what motivates our approach, which started from looking at real-time edge AI use cases in science. And so these science use cases for real-time AI near sensors are very numerous. So in my field, I work at one of the experiments at the Large Hadron Collider, where we collide protons at every 25 nanoseconds at nearly the speed of light. And we analyze and read out the collision measurements in real time with on-detector ASICs and filter the collisions with off-detector FPGAs. AI is also being used to steer these beams in the accelerator complex, for example, at Fermilab, using techniques like reinforcement learning. In the related field of neutrino physics, detectors deep underground actually need to detect and filter neutrinos from supernova and potentially alert other experiments, and again, in real time. And similarly, gravitational wave detectors like LIGO can detect astronomical events like neutron star mergers and also quickly alert other observatories in this expanding field of multi-messenger astronomy. And finally, electron microscopy and other experiments can use real-time AI to control their experiments and perform sort of a fast feedback loop. So of course, to deploy these real-time edge AI algorithms in these systems, we often need to develop specialized versions of them. And the way we accomplish this is through this principle of co-design, which is of course the intrinsic development loop between the algorithm design, training, and hardware implementation. So the common tools of the trade, of course, include compression, where we try to shrink the algorithm as much as possible while retaining performance. So we want to reduce redundant operations that are not needed. Quantization, where we reduce the precision of the operations. And parallelization, so where we balance essentially how fast we need the result with how many resources we have available, or the power, if there's power constraints as well. So with these aspects in mind, we developed this tool, hls4ml, for scientists or machine learning experts to translate their algorithms into RTL firmware. So the design process looks something like this. So you have your usual machine learning software workflow where you may design a model in Keras, TensorFlow, or PyTorch, or some other machine learning library. Often you'll compress this model and iterate on that. Then you can use this stack, hls4ml, to actually convert this to a high-level synthesis project, or HLS project, which can then be tuned. The configuration can then be additionally tuned from there. And then finally, from there, you can export this HLS design to custom firmware that targets different FPGAs or ASICs with different flavors of HLS compilers from Xilinx, Intel, and Mentor. So that's the sort of overall big picture. So let me go into a little bit of the features of this package, hls4ml, to give an idea of how it works. And so the package itself hinges on our internal representation of the model, where which we call this HLS model, and model converters basically translate from these different libraries into this HLS model representation. From there, we have these configuration handles that help you tune the performance. So, basically the basic resource versus latency trade-off, as well as other settings like the precision. Then there are optimizers that essentially detect when the model can be optimized, such as fusing nearby adjacent layers like batch normalization. And then finally, the core of the package is in these different backends, which write out HLS projects targeting these different vendors' FPGAs like Xilinx and Intel, as well as ASICs, which we do through Mentor's Catapult HLS. And for each of these different HLS or targets, we have this library of optimized neural network HLS operations, which can be customized for each of the different flavors. And in addition, there's implementations for different strategies. So depending on if you're targeting lower latency or lower resources, there can be different versions. And finally, there's sort of useful utilities that are built in, such as model profiling and visualizing the model, which can help you essentially make good configuration choices by scanning what is the distribution of the weights and inputs and outputs that you see in the model. So just to give a peek of what this looks like, we have also fully integrated with a library called qkeras, which allows you to build quantized versions of keras models with drop-in replacement layers. So this is just building a qkeras model, and then you can do a quantized version of the prediction. And then to show sort of what the conversion with hls4ml looks like using this Python API, you can see there's a few different commands. One is the configuration, which is built and can be automatically built from a model. So, looks at and can be then customized with the parallelization, the precision, or the strategy, since this is essentially just a Python dictionary that can be modified. Then we actually convert this to our HLS model representation, which actually also creates the HLS project that you can then inspect the actual HLS code if you want. Finally, then we actually can compile this model, which gives you actually access in Python to the quantized predictions. And then finally, you can actually build the model, which so synthesize it into RTL using the HLS compilers from different vendors. So to kind of demonstrate what are the capabilities of hls4ml, we can sort of look at one small use case, which is a small neural network that we often use in the LHC, in an LHC application, to identify different kinds of particle showers, which we call jets, which is a common task that we do in the FPGA filter system. And so this small neural network, essentially fully connected neural network, just looks at 16 different inputs and try to determine whether that data belongs to one of these 5 categories of jets. And as you can see, this small neural network can actually get up to very good accuracy for this task. And so what we do here is basically we show a comparison between what it looks like if we do sort of a naive post-training quantization, where we see that we need 14 bits on the FPGA to reproduce the full accuracy of the model. But with quantization-aware training with qkeras, we can actually get down to 6 bits, and we see that the FPGA does reproduce that accuracy, which of course means that we need a much smaller fraction of the resources on the FPGA. So this is showing the resource usage for the LUTs, the flip-flops, and the DSPs as a function of the bit width. And by going down to 6 bits, we of course can use much less. And since the area and power also scale quadratically with bit width, we can also get down to lower power. An additional approach that we've been exploring is actually quantization-aware pruning, which is an iterative pruning on top of the quantization-aware training. And so for this specific neural network example, after QAP, this 6-bit model can be pruned by 80%, which achieves another factor of reduction in bit operations, which is a sort of a way to measure the hardware complexity. And this study was actually done with Brevitas, which is a PyTorch-based quantization library, which we're planning to integrate with hls4ml soon. So just to demonstrate the ability to control the parallelization, there's another benchmark that we looked at, which is this MLP for identifying MNIST handwritten digits. And again, this was just chosen to probe a large range of possible parallelization strategies. As you can see, it's a very accurate model, even though it's very small. And the way the handle that we have in hls4ml for controlling the parallelization is what we call this reuse factor, which can be applied heterogeneously for each layer. And what it does is it basically controls how often you reuse the DSP multipliers in each layer. So as you can see here, as you increase the reuse factor, which is on the x-axis, you're able to decrease the number of DSPs that you need from the FPGA in order to run this model, because you're essentially reusing them for the multiplications that need to be done in each layer. So there's a nice trend that you can see going as it goes, increasing the reuse factor. So a third benchmark that I wanted to show is the CNN. So this is a CNN for classifying digits from the Street View house numbers dataset. And the interesting thing to point out here is that we actually used um, a capability of this package called AutoQKeras, which can be used to actually optimize the precision heterogeneously by layer according to the estimated energy usage using these Horowitz estimates. And what we find is that the estimated, we are able to basically find a configuration which should minimize the energy usage. And moreover, it can also be pruned additionally by another 50% with no loss in performance. And so this model ends up having 88% accuracy with a small energy usage. Okay, so with that in mind, so far I've sort of described the generic features and the flexibility of hls4ml that are all useful for real-time AI applications in science. But I'll turn to now to talk about how we're expanding into thinking about lower power and how we can use this tool for various use cases that might be important to this community. And so to do that, the best way to show you is to talk about a real-life application at the LHC, which is a data compression ASIC. So the picture on the bottom left is a silicon module, so one of thousands that are part of this new detector that's being built. And the ASIC itself has the job of taking 366 bits that are coming in from the detector at 40 megahertz and reducing it by a factor of between 2 to 7, depending on some specifics of the detector geometry. And the way we do this is using essentially an autoencoder, so using the encoding part of the autoencoder to do this. This also allows us to reconfigure and retrain it if conditions change. So the way that we develop this is actually using a combination of some of the things I've talked about already. So we use QKeras to actually develop the network with quantization-aware training. We use hls4ml to actually convert it, and Catapult HLS to convert it to HLS and RTL firmware. And then we also actually use this TMR for the triplication to actually make it robust to radiation, so make it more radiation tolerant. And so in the end, what we see is that using this workflow with these different tools, we're able to reduce the power by quite a bit and area, as well as maintaining the good performance with respect to a reference network that we started with. And we're able to do this fairly quickly because of the fast sort of design cycles. And so this is mostly optimizing the compression and the quantization. And what you can see here is that the ultimate power that we achieve is 48 milliwatts for this 65 nanometer technology. And again, it's 40 million inferences per second because of the high data rate. So that's one reason why you see it's only down to 48 milliwatts. But the energy per inference you can see is 1.2 nanojoules. Okay, so then again, we're interested in exploring applications of hls4ml for low-powered, tiny machine learning. So right now, we're actually looking at applying using off-the-shelf FPGA development boards and using hls4ml to see how low power we can achieve. And so our aim is to provide functional examples from the tinyML perf benchmarks. So for example, anomaly detection and image recognition for the community to run on these kinds of off-the-shelf hardware to give people an idea of how to use hls4ml for low power applications. Okay, so to quickly summarize, so real-time low power AI can accelerate our science by allowing us to test hypotheses faster and enhance the performance of our detectors and potentially save data that have been overlooked. hls4ml is our again, expanding open source toolkit for translating these algorithms into hardware aimed at supporting scientists. And the ultimate goal is to fully integrate all the best practices for co-design and AI plus hardware in this nice all-in-one workflow. I talked about the current applications in the talk, and ultimately we're hoping to go towards smart sensors, autonomous detectors, and accelerated loops for our experiments. So thank you.
Okay. Yeah. So Javier, so you started. I mean, you had this, nice tool flow from algorithm all the way to, actual FPGA or ASIC hardware. So let's say, for a given network, there are many like FPGA implementations and ASIC implementations. So, I mean, you talked about the baseline kind of improvement, but is there some comparison that you could provide on how, your hardware compares to other hardware reported in the literature for similar or same kind of models?
Yeah, it's a good question. We have done some comparisons. So for instance, with other tool flows, so for example, Fin, the Xilinx tool flow, we've done some comparisons with the same kind of model and looking at that. But yeah, we have not done a comprehensive, so we should sort of update and do kind of a comprehensive comparison with um, other tool flows. The main point is that we're, developing a tool that can really be used for a variety of models, and we're not sort of optimizing for one specific model, let's say.
Okay. There are a couple questions on the event tee. So the one is, are you planning to include NAS, neural architecture search in the loop?
Yes. Um, so to some degree, the auto QKeras is doing some form of, sort of a neural architecture search in the sense of looking at optimizing both the number of, well, it's mainly optimizing the precision, but you can also use it in combination with like a Bayesian optimization to optimize things like, number of neurons, number of layers. And this is something that we are actively and have some results for combining Bayesian optimization with like quantization search as well.
Okay. And I think the second one is kind of similar to the first one, but it was, does hls4ml have design space exploration? I guess you talked about the algorithm in terms of NAS, but in terms of hardware, their design space is actually, massive too. So do you do some kind of design space exploration on the hardware side as well?
Yeah, so this is sort of the point of the configuration step. So the configuration step lets you sort of choose, make choices for the uh, whether you want to go for lower resources or lower latency. And so that can be automated as well. And we have like created some scripts around that to automate that. So yeah, so there is definitely ways to do search on the hardware side as well as on the model side. Yeah.
Okay. And maybe final quick question is quantization done also when you're doing backpropagation during the training?
Yes, no, so it's not. It uses the straight through estimator. So just quantizing the forward pass.
Okay. So I think Tinesh, I know you had some questions. Do you want to ask a quick one, or since it's 12 p.m., we should move on to the next?
Right, we can move to the next one.
Okay.
Yeah, but
Okay.
please send me email if you have more questions. I'd love to discuss.
Sure.
Okay. Thank you, Javier.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML, Silicon Labs, Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.